Numbers are the language of the cosmos. They unlock secrets of the universe, from the tiniest atom to the largest galaxy. We use numbers every day, counting objects, measuring distances, and tracking time. In the world of mathematics, there exists a special category of numbers called irrational numbers. Irrational numbers cannot be expressed as a simple fraction of two whole numbers. Imagine a pie cut into equal slices. A rational number would represent a whole number of slices, like half the pie or 2/3. Irrational numbers, however, are like trying to cut a piece of pie that can never be divided evenly, no matter how small you slice it. These numbers continue infinitely without repeating, their decimal representations stretching on forever like the vast expanse of space itself. This infinite, non-repeating nature sets them apart from their rational counterparts and makes them both fascinating and essential to understanding the true fabric of mathematics. One of the most famous irrational numbers is the square root of 2, denoted as 2. This number represents the length of the diagonal of a square with sides of length 1. Imagine drawing a line straight across the middle of a perfectly square piece of paper. The length of that line is 2, a number that has intrigued mathematicians for centuries. Its significance goes beyond simple geometry. The discovery of 2 challenged the ancient Greek understanding of numbers, who believed that all numbers could be expressed as fractions. To assess irrationality opened up a new realm of mathematics, revealing the existence of numbers beyond the realm of simple ratios. This groundbreaking realization revolutionized the way we think about numbers and paved the way for countless mathematical discoveries. To understand why 2 is irrational, we turn to a powerful tool in the mathematician's arsenal: proof by contradiction. This elegant method involves assuming the opposite of what we want to prove, and then showing that this assumption leads to a logical inconsistency. Imagine a detective solving a crime. They might assume the suspect is innocent, but then find evidence that contradicts this assumption, proving their guilt. Similarly, in mathematics, we can prove a statement to be true by showing that its opposite leads to an impossible conclusion. This method of proof, often called reductio ad absurdum, Latin for reduction to absurdity, is a cornerstone of mathematical reasoning. It allows us to explore the validity of statements by examining the consequences of their opposites. To prove that 2 is irrational, we begin by assuming the opposite, that 2 is rational. This means we can express it as a fraction a over b, where a and b are whole numbers and b is not 0. We can further assume that this fraction is in its simplest form, meaning a and b have no common factors. If 2 equals a over b, then squaring both sides gives us 2 equals a squared over b squared. Multiplying both sides by b squared gives us 2b squared equals a squared. This tells us that a squared is an even number since it's equal to 2 times another whole number. If a squared is even, then a itself must also be even since the square of an odd number is always odd. So we can write a as 2k, where k is another whole number. Substituting this into our earlier equation, 2b squared equals a squared, gives us 2b squared equals 4k squared. Dividing both sides by 2 gives us b squared equals 2k squared. This tells us that b squared is also an even number, meaning b itself must be even as well. But wait, we initially assumed that a and b have no common factors. Now we've shown that both a and b are even, meaning they both have a common factor of 2. This contradiction tells us that our initial assumption, that 2 is rational, must be false. Therefore, 2 cannot be expressed as a fraction, and is indeed an irrational number. This elegant proof, discovered over 2,000 years ago, stands as a testament to the power of mathematical reasoning and the enduring fascination with irrational numbers.